a tree using some search algorithm, depth first probably, or some variation of it, looking for a goal state. With adversarial game search, it's going to be similar, but you have to take into account that there's going to be counter moves that somebody else is going to be able to make. So I'm going to formulate everything as two-player games using trees. We'll talk about evaluation functions, minimax and alpha beta, and then actually some just stuff at the very end, some slight variations about what would happen if there were dice rolling or some sort of chance involved, and what would happen if there were more than two players. We'll kind of generalize it a little bit. So for two-player games, what are some classic two-player games? We've got tic-tac-toe, Connect Four, checkers, chess. You could potentially even throw poker in there or something like that. So these are classic two-player games. We need to think about how to formulate these as a problem that we can do artificial intelligence with. So one thing we can do to start with, we'll treat the initial state of the game as the root of the tree, and we're going to have a first player. We're going to call the first player Max. Now that player is going to move. They're going to have several moves to choose from. These moves, each move is going to create an edge to a new state of the game, which will become the next node. And so we're going to build up a tree this way. Now the second player has counter moves that they can make based on the possible moves that Max made from the initial state. And so that second player we're going to call Min, and the reason that these players are called Max and Min will become clear later on. The second player is going to choose their possible moves to counter move whatever moves Max has possibly made. And so you can kind of see there's going to be moves and counter moves, and you can see the exponential blow up. So here's an example of this. Here, suppose this is the state of the board right now. Well, it's X's move. Let's say that X is Max. Well, X has three possible moves, so there's three children to this node in the tree, which would lead to three different states. Now, from each of those states, the O's would have two possible moves. So we've got these two moves, these two moves, these two moves. And then from that state again, we'd get back to Max. Max would only have sort of the one move, and then this gets us down here to the bottom. We're now at the terminal nodes of this particular tree. And so if we kind of imagine, oops, that's not what I meant to do, that this node is actually going to be a child of some other nodes, you can kind of imagine walking this back up and down the tree. So that's the general idea. We're going to turn this into a tree where each node contains the current state of the board at that particular time. Now, there's some questions. How does this differ from a puzzle-solving search problem? What's the goal of a move in a two-player game? And there's this open question, can we search all the way to a terminal state? So let's kind of go through each one of these. So how would this differ from a puzzle-solving search problem? Well, puzzles don't have counter moves. You know exactly what the state's going to be after you make one move, and then when you make the next move. Now, in a two-player game or an adversarial game, you don't know. You're going to make a move, and then the opponent's going to get to make a counter move. Now, we don't know what counter move that they might make, but we know what all the possible counter moves would be, so we don't know exactly what the state would be, but we can maybe try to guess. Now, what's the goal of a move in a two-player game? Question number 2 here. Well, you want to find the best move that maximizes my position, no matter what my opponent does. And so this, to a large extent, depends on how we're going to evaluate the position, how I'm going to evaluate the position, how I will assume that my opponent will evaluate the position as well. And then can we search all the way down to a terminal state? For tic-tac-toe, we can, and you can easily write a program that will never lose at tic-tac-toe, and playing against another program that's also perfectly written to play tic-tac-toe, that program will never lose. You'll tie every single game. Can you search all the way to a terminal state in general? No, not for interesting games. The possible combinations of moves for games like chess are just way too big. Even Connect 4 is quite big, and Go is even bigger than both of them. And so you can't actually, in general, search all the way to a terminal state. Why are we not going to the next? Are we frozen? What's going on here? There we go. Wow, oh my gosh. Okay, there we go. Okay, so we cannot always search all the states exhaustively. So chess has too many possible combinations. Checkers is even pretty big. Even Connect 4 is fairly big. We can only do simple games like tic-tac-toe. but that's not really very interesting. But we would like to build programs that can play checkers and they can play chess without actually being able to search all the way to the terminal state and make sure you make a perfect move. So we need some sort of a heuristic. So this is called an evaluation function. What we need to do is come up with a single number that we can assign to any board state to describe its value to the two players. So this is why the players are actually named Max and Min. Max wants to maximize this number, so bigger numbers are better for Max. Min wants to minimize the number. And so we can think of some example evaluation functions, tic-tac-toe, I don't know, could be the number of possible ways I could win or lose or something like that based on this move. Connect 4, I don't know, could be the same thing. Checkers and chess, you can just do the differentials of the pieces. Hexagon's a really cool two-player game. I wish I had the animation. I'll put a link up to it. It's fairly cool. You can play it online. So tic-tac-toe, connect 4 could be number of ways I win. Am I about to lose? Maybe I privilege. It's a better move for me if I can win 2 possible ways. Checkers and chess, you could do number of pieces remaining, value of remaining pieces, differential in remaining pieces. So if I take my number of checkers and subtract your number of checkers, and I'm whatever number I end up with, if it's positive, that's good for me. If it's negative, that's good for you. So if I'm Max and you're Min, that actually works really well. You could do the same thing with chess, sort of the piece differential. You can also poison some moves by assigning a highly negative or a highly positive value so that some positions that are known to be weak so that you don't want to make those moves. So in checkers, there's moves called the dog hole and the dust hole. These are places you don't want to move into. So you can sort of poison those moves by giving them very, very bad set your evaluation function so it returns a very bad number for you for those particular moves. You can imagine the same thing in a number of other games. So Minimax, once you have an evaluation function and we've built up a tree, well, we can actually store the value of the board state in the board state at each node. We can actually start running an algorithm to try to figure out, well, what's the best move that I should make. And so the simple algorithm for this, well, search as far down the tree as you can using depth-first search. The reason for depth-first search, of course, the time is exponential in the worst case, but the space is polynomial. The values percolate back up the tree, and you're going to pick the best move that ensures the best outcome regardless of what the opponent does. This is called Minimax. So here's the idea. Max's scores will be listed in red, Min is in blue. Max is going to make the first choice here. So Max has 3 possible moves. That leads to 3 possible states. Now Min gets to make 3 possible counter moves from those states. And then from those counter moves, Max gets to choose again. Now maybe we can't look any further. So what we're going to do is just, from Max's perspective, evaluate the board state at this point. Maybe we can only look ahead 1, 2, 3 levels. Would say the term that they use in artificial intelligence is how many plies. So this is 3 ply deep, P-L-Y, and the plural is plies, P-L-I-E-S. So you see that term in artificial intelligence a lot. So I can't look farther. Maybe this game is too complicated. There's too many possibilities. So I can only look 3 moves ahead, 3 plies ahead as the Max player, and then this is what the board state would look like there, and these the evaluation function has been applied to those board states. So I'm going to search all the way down. I'm going to do depth-first search. I'm going to evaluate all of these possibilities, and remember, this is a Max move. Well, 5. That's the best that I can do. I have 3 possible moves, and I evaluate the boards to be 2, 1, and 5. Well, I'm Max. 5 is the best, so I'm going to put that here. So that's what Max can expect the value of C1 to be. Now, similarly, Max can expect the value of C2 to be 11, because Max would get to pick at C2. So the value there's 11. And at C3, the value would be 8. So those are the those are the outcomes for C1, C2, and C3, because Max is going to pick. If Max picks here, Min's going to pick. Min will have to make one of these 3 choices to get to one of these 3 states. Max will have 3 possible moves from each of those states. This is what Max figures the board will look like at those states. So Max has these 3 possibilities. Max would like 11, but B1 is a Min choice. Now, we have to assume that Min and Max know the same thing. There's no hidden information in these games. This is like, checkers or chess, you can see all the pieces that are on the board. So Min's going to look at this and be like, well, I'm Min. I want the lowest score. So if I make this move, well, I know Max would make this move, and I'd get stuck with an 11. I don't want an 11, and I don't want an 8. I'm going to pick a 5 because that's best for me. That's the smallest value that Min can get here. So the value at B1 is going to be 5. So if Max makes this move, Max can expect a value of 5 because Min knows that Max knows everything that Min knows. So even though there's these other two moves here that might look better for Max, Min is going to make this move to make sure that no matter what move Max makes, it's not going to be any worse than 5, right? So Max would like these things. Min is never going to let that happen because Min would never pick one of these moves and let Max have one of these higher values, this 11 or this 8. And then we will do the same thing here. So we've got 4, we've got 11, we've got 2. But remember, this is a Min node, so we can expect the value at B2 to be 2, right? Because Min is going to go ahead and make this choice, knowing that Max would pick this choice, and so Min will end up with a 2. And then similarly over here, 3, 11, and 5 would be those values. So Min can expect a 3 there. And so this is what Max is left with. Max has a 5, a 2, and a 3. So Max is going to pick the one that maximizes the outcome here, which is, of course, 5. So at this point, Max can expect for this node A that, Max will pick in this direction, knowing that no matter what Min does, Max is going to end up with a 5. Max wouldn't pick one of these other ones, because even though there's some great numbers down here, 10s and 11s and things like that, because Min gets to make a counter move, Min is going to stick Max with either this 2 or this 3, and Max doesn't want that, so Max is going to make this choice to try to go ahead and do no worse than 5. In fact, Max will do exactly 5. So that's Minimax. So there's some questions here. This is based on depth first search, DFS. Well, why DFS? Well, I mentioned before the runtime complexity and the space complexity. If you think back, the runtime complexity of depth first search, breadth first search, really any of these algorithms is going to be exponential, because you're going to be, exploring all these possible nodes, and the nodes are exponential. You've got B as your branching factor, D as your depth. That's big O of B to the D in terms of the runtime. But the space complexity of DFS is only polynomial. It's going to be B times M, where M is the max depth that you are searching. So that's actually better. And so since we can't search all the way to the terminal states, of course not, we can only search part way down. The algorithm that Minimax uses, it's based on depth first search, but it's not actually going to be depth first search. If you just run a naive depth first search, you're going to just run forever, essentially, more or less forever. You're going to run for an exponential amount of time. So as you scale up to large problems, it's basically going to run longer than you're going to be willing to sit there and wait for it. So what you're going to do is what's called depth limited search. You're going to do depth first search with Minimax for a depth of 1, and then for 2, and then for 3, and then for 4. And you're just going to keep gradually expanding how far you're able to search until either you run out of time or until you've searched as much as you can, as deep as you can for the memory that you have. And you know that if you were to do a search again, you would totally fill up your memory because you have an approximation of what the branching factor and the maximum depth that you might be able to search, given that branching factor and how much memory you have. So we say depth first search, but we really don't mean a naive regular depth first search like you've implemented for your graph lab. That would run forever. It's actually a depth limited search where we gradually increase how deeply, how many plies we're able to go, how much depth we're able to try to search until we get to a point where we've run out of time or we know we're going to run out of memory. Now, there's another question related to this. Can we do better? Do we have to search all the possible subtrees with Minimax? And of course, we don't. So the idea, you don't want to evaluate any more nodes once you've found a max that's bigger than the min of the maxes available elsewhere. Sounds confusing, but this will make more sense when we do an example. So remember, min will choose the min of all available maxes, right? And Max knows this. So if we think about that algorithm we just did, well, we evaluated this first subtree. We decided that that was a 5. Now we start evaluating the second subtree, C2. We see a 6. Well, at that point, what do we know? Well, we know that B1 is a min node, so min's going to choose the smallest thing it can find. Well, we know that there's already a 5, so min is not going to pick anything bigger than 5, right? If C2 and C3 are, a million and 10 million, well, who cares? Min at B1 is going to pick this move here, C1, going to make sure it's 5. So once we see this value in C2 here, 6, that's bigger than 5, it actually doesn't matter what these other two nodes are. They could be negative infinity, they could be positive infinity. It actually doesn't matter at all, because min knows that max at C2 is going to be picking. Well, if there's a 6 here, max is never going to pick anything less than 6. So the value of C2 can't be less than 6. But at B1, we know the value at B1, because that's a min node, can't be bigger than 5. Min's never going to pick anything bigger than 5. So once we see at C2, we're going to have a value here of at least 6, and we know that min is going to pick nothing bigger than 5. We don't even need to look at these other nodes. Doesn't matter what they are, because min's never going to let max have them. So we can actually prune that with alpha-beta pruning, and we don't even have to look at those at all. Now, do we have to look at C3? Well, at this point, we know that there's a 5 here, we know that there's a 6 here, so we know that at B1, we're not going to have anything, since B1's a min node, we're not going to have anything that's bigger than 5. Well, we don't know what C3 is. It could be smaller than 5, in which case min would stick us with C3. It might also be bigger than 5. We actually don't know, so we have to look at it. But again, as soon as we see that 8, we know that max is not going to pick anything smaller than 8. Min, on the other hand, is not going to let max have anything that's bigger than 5. So once we see that 8, bam, we prune out these other nodes. We don't have to look at them. It doesn't matter what they are, because they're never going to be chosen. So that lets us do some pruning over there on that B1 subtree. Now, what's really fascinating about this, actually let me back up one, we'll kind of walk through this. When we start evaluating the B2 subtree, right, we get down here to C4, we see a 3, a 2, a 4. We now know that there's a 4 available at C4. Well, what do we know? Well, we know that B1 is going to be a 5. We know that A is a max node. If B1's 5, max is never going to pick anything smaller than 5. Once we see 4 here, B2's a min node. Min's never going to pick anything that is bigger than 4. Well, max is never going to pick anything smaller than 5, which means the value of B2 has to be less than or equal to 4, right? Because min knows there's a 4. Min's not going to pick anything that's bigger than 4. Well, max already could get a 5 on another subtree, in the B1 subtree. Once max knows that min's going to stick max with something 4 or less at B2, who cares? We don't have to look at the rest of it. So once we see this 4 here, we can actually prune both of these subtrees without even looking at them. It doesn't matter what's there. Min's not going to pick anything bigger than 4. Max at A is not going to pick anything less than 5. Bam, prune it. Don't even have to look at it. The rest of B2 is irrelevant. And then similar for B3. As soon as we see this 3 being less than 5, we know min's never going to pick anything bigger than 3 on this subtree, because min could do better. Max, however, has a 5 available. Max is not going to pick anything that is less than 5 anywhere, so once we see that there's a 3 here, we don't even have to look at the rest of it. We can actually prune it. So it turns out we can actually evaluate considerably fewer nodes and subtrees using alpha-beta pruning than if we just do naive minimax. It's actually really, really awesome. So how would a sophisticated chess-playing program or some other fancy adversarial artificial intelligence program improve on Minimax with alpha-beta pruning? Well, alpha-beta is actually a really good algorithm. You can get more memory, which means you can fit more nodes, which means you can probably look a little bit deeper. If I can look 10 moves ahead and you can look 11 moves ahead, you're probably going to win because you can look a little bit further ahead. So I'm sort of cutting my search off before you are. You're looking one move ahead. You're going to have a little bit more information, a little bit more accuracy when you start running your alpha-beta pruning. Another thing that in practice these adversarial AI programs do is they have lookup tables. So if ever I see the board is in this state, I know that there's some sequence of moves I can make to win the game based on looking at historical games that have been played or analyze. This is true for endgames in chess. A lot of programs will have an endgame library. They'll also have an opening move library. You know that, once your opponent makes this move and puts the board into this state, well, you know that the right things to do throughout history have been this sequence of moves, so you're just going to go ahead and do that. Another thing you can do is specialized hardware. So this is definitely true for chess playing robots. You can have special chess playing robots, chess playing AI programs. You can have special hardware that very succinctly is able to encapsulate board state and things like that. You could have better evaluation functions, more sophisticated evaluation functions. You could have evaluation function lookup so that you're not actually running an algorithm where as soon as you see the board state, you can just kind of look up that that's a special board state, that we know that there's some sequence of correct moves to make. But all of these are just optimizations. The core idea is still there. It's a board state. You have an evaluation function that can look at any board state and decide how good is it, produce a number. How good is it for max? How good is it for min? You put this into a tree situation, you search ahead, and then you can use Minimax and alpha beta pruning to try to select the move that is the best for you, regardless of what counter moves the opponent is able to make in the process. And that's kind of the core of adversarial artificial intelligence and has been really back to the 60s. There's a lot of optimizations, all of this stuff plus some number of other things, but those are just that, they're optimizations. I don't really think there's really been any changes to the core of how these things are going to work. Now, what about two-player games that involve chance? Backgammon, Risk, Settlers of Catan, things like that. Well, you have to introduce a chance layer where the outcomes are going to be weighted by their chances of happening. And this actually explodes the branching factor a little bit because you have to take into account possible outcomes based on the different die rolls or the different, whatever the random factor, the random chance event is. But it doesn't actually complicate the algorithm very much. It's still the same algorithm because you don't have choices to make with those chance layers. It's just that there's a weighted chance that each of these things happens, and so you just take that into account when you're running the algorithm. So this algorithm is usually called Expectiminimax. Sometimes it's shortened to Expectimax. The expect part because you're weighting things with the expected outcomes. So, here's an example of this. I've got a choice to make here. If I choose here, well, a random event happens, a die roll, cards get drawn, whatever, and I know there's a 0.7 that I get 3, and 0.2 that I get 12, and 0.3 that I get 8. So what I do is I weight all those possible outcomes by the likelihood that they happen. I add it all up, and I end up with 6.9. Do the same thing over here. I end up with 3.6. So if I'm a max player at this node, I would pick this move because on average I'm going to end up with a better outcome than if I picked over here. Now, of course, in practice, I could pick over here and end up with this 3, whereas, had I picked over here, maybe I would have ended up with the 5 or something like that. I mean, I don't know. I'm just going based on, well, what are the likely or probable outcomes? So even though I went over here, I still could get stuck with this 3, but on average, I'm going to be better off. And so, here's sort of another example, which I'll probably just turn into a clicker question. So Max has got a choice to make here. What subtree should Max choose? Well, we can sort of do the weighting. I've got, I'm on average going to get 0.5 chance I get 5, and 0.5 chance I get 20, and then so on. So it's, to go back a slide, it's basically this, but I've done a slightly simplified example. Probably what I'll do is turn this into a clicker question. So the last thing is, what about multiplayer games? So what we've been looking at for these adversarial games has really just been two-player games. Well, you can have games with more than 2 players, Risk, Settlers of Catan, things like that. So how would we handle multiplayer games? Well, it's actually the same algorithm, but what you have to do is, instead of being able to think of it as one number, higher is good for max, lower is better for min. If now there's 3 players, usually what you do is you just evaluate the utility of the board state for each player, and then you set it up as a tuple. So this would be for a 3-player game. Here's a tuple. So this board state is better is best for player 1, because player 1 evaluates the board and says that's worth 8 for player 1, it's worth 7 for player 2, 6 for player 3. This would be really good for player 2 because it's 7 for player 2, but lower for player 1 and 3. And then this is actually really good for player 3 because even though the evaluation function says that player 3's only got a 0 here, well, it's actually much worse for player 1 and player 2. And so you would have to just come up with an evaluation function that can produce these tuples for the board state, and then you would have to do all the decision-making based on the tuples. And the branching factor also explodes again as well, because now you've got a player 1 choice, a player 2 choice, and then a player 3 choice. So you're sort of rotating between all of those when you're building out your tree. And I think that's all I have. Awesome.